Okay, so next example we've got here. I got this tube here. Outer diameter is 4 inches. Inner diameter is 3 inches. It's made out of steel, so 29 times 10 to the 6 psi is its Young's modulus. Our I, again, just based upon the I of the outer diameter minus the I of the inner diameter, brings us to 8.59 inches to the fourth. And we want to find what the reaction is and the maximum bending stress. And the loading situation is as such. So it is mounted to the wall at A. It has a 1,800 pounds per foot distributed load between A and B. That's over a 3-foot section or a 36-inch section. There's another 36 inches. Then it's mounted to this thing here. It's a, if it's a fixed connection, but that fixed connection, that wall that it's mounted to, is allowed to move in the X direction. And essentially that's just a little fiction that they added in order to allow us to solve for the X reaction at A. So anyway, yeah. So quick free body diagram. I'm going to have a support in the Y direction at C and at A. And then both A and C are going to have moment reactions as well. So drawing those on here. Going to have a reaction A in the X direction, which is obviously going to be equal to 0. And what else do we have here? So that's about it. So we're going to use the method of superposition to break this up into kind of 3 separate loading situations. So we're going to keep the cantilever beam mounted at A, and then essentially what we're going to do is we're going to have a separate, a distributed load that goes halfway across. We are going to have a point load at the end, that's for CY, and then we're going to have a moment at the end. So all those can be taken from Patel's. So I got C4 for Patel here for the distributed load. Got C1 here for the point load, and we got C6 for the moment. And each of those are going to cause a certain amount of displacement and a certain amount of tilt at the end as well. And again, just the one thing I want to keep in mind here is that you want to kind of ensure that when you're looking at these tables that you kind of translate them to your coordinate sign conventions. So again, when we look at the C1 here, we have what we define as a positive load, and that's going to be causing what we call a positive displacement. So kind of the opposite situation of what's going on here. For C4, again, we would call this a negative load, so it's going to cause a negative displacement. Again, here, what they've drawn a negative moment at the end there, and it's causing what they call a positive displacement. So essentially, I'm kind of flipping it. With the situation that we've got is we're assuming it's a positive moment that's being drawn on there, so it should cause what we, it should cause a positive displacement and a positive angle as well. So let's flip back to here. So again, keeping both of these as positive due to the fact that the direction was flipped there. So anyways, what sort of compatibility condition do we have for this? Well, we know that the displacement at the end here needs to be equal to 0, and we know that the angle at the end also needs to be equal to 0 because it's a fixed connection, so it needs to stay kind of flat there. So we can just kind of sum those up. So we got the displacements that we can add up, and we've got the angles that we can add up. So adding up the displacements gives us this, just subbing our various the values that we've got into those three equations. Gives us this, which we can solve, we can solve for for the reaction in term the moment reaction at C in terms of the vertical reaction at C. So the vertical force reaction at C. And then same thing for these ones here. Take those, plug the values in. I'm not going to talk our way through those. Again, I just cancel out EI when we can because it's simple. But it gives us this, which again we can solve for MC in terms of CY. So we got MC in terms of some value, some constant, and CY. Got MC in terms of some constant and CY. Well, we can make those two equations equal to one another, which allows us to solve for CY. So that gives us a CY of 1,012.5 pounds. So, based upon that, if we know CY, we can also solve for MC. So using this first equation here allows us to find the MC is going to be equal to negative 20,250 pound-inches. So just redrawing our free body diagram here. Still got the two unknowns, AY and MA. So simple enough to find it at this point. So we got the sum of the forces in the y direction. So AY minus the resultant of this one here, the 150 pounds per inch times 36 inches, gives us that. And plus the reaction at C, the 1012.5 gives us an AY of 4,387.5 pounds. And then we can do the same thing for the moment, just taking the sum of the moments at A. That's going to be equal to the moment reaction at A minus that resultant force times its moment arm plus the reaction at C times its moment arm and minus the 20,250 pound-inches, which is the moment reaction at A. So that allows us to solve for the moment at A. That's 44,550 pound-inches. So we got enough information to start doing our diagrams here. So the shear, it starts at 0. the reaction at A is a positive load, so it jumps up to that amount, for 4387.5, and then it starts dropping down. So it starts dropping down at a constant rate of negative 150 pounds per inch over a 36-inch span. So the drop there will be the 5,400 pounds that we had originally solved for, which gives us a shear value at this point of negative 1,012.5 pounds, which stays constant until we get here, and then we get to the reaction at C, and it jumps us back up to 0, which is what we expect to happen. So, fairly straightforward there. I'm also going to point out the spot here where this shear crosses the x-axis. It's going to be we can solve for that just by using the equation. In this area, the equation of this line's 4387.5 minus 150x. So the point at which that's 0 is going to be 4387.5 divided by 150. So that's at 29.25 inches. So, and then onto our moment diagram. So again, we've got our reactions as well, so we need to keep those in mind. So we've got reactions at both ends, so we're not in one of those situations like a pinned connection where we'd expect where we expect it to be returning to 0 at either point. So just keeping in mind the way the moment diagrams work is that when you're moving from left to right and you encounter a positive point moment, that causes your moment diagram to drop down. So starting at 0, we immediately encounter a positive moment of 44,550, which drops us down to an internal moment of 44,550 pound-inches. So again, and we can see that this is the case, that's negative, because if we take a section just zoomed in right there, we got this bar here, there's a little section of the bar here, and we apply a positive moment on this side of that amount, and again it's going to have a reaction. It's going to have a reaction on this end. So again, doing that to this bar, that's going to cause it to kind of deform into a frowny face. So that's a negative. That's a negative internal moment. So yeah, we're negative in here, and then we're starting out from negative, and then we're increasing until we hit this point here. So the magnitude of that increase is going to be equal to the area under this curve. So 4387.5 pounds times 29.25 inches divided by 2 gives us the increase. So 4387.5 times 29.25 divided by 2. So that's going to be an increase of 211 pound inches. So that added to our negative 44,550 pound inches gives us a maximum bending moment at this point where at that point where the shear graph crosses the x-axis of the what do we got here? 19,617. And then we're able to figure out kind of where it starts to level off there. So that is going to be that's going to be a decrease from that maximum based upon the area of this little triangle here. So the area of that triangle there is just going to be the 1012.5 pounds times this distance here, which is going to be 6.75 inches, divided by 2. So that drops us from our 19,617 down to 16,200 at the midway point of this beam. So that midway point, again, I would like to emphasize, is not the maximum bending moment. You can rarely assume that that's the case unless it's a very simple loading situation. So like it will be the case if you're supported equally on both sides and there's a point load in the middle, or something similar to that. But if it's anything slightly more complex, we cannot assume that the maximum is going to be in the middle. So you definitely don't want to be falling into that trap, because if you had done so, then you'd be significantly underestimating the amount of bending stress which occurs in this beam. But anyways, so at that point, we're at 16,200, and then it's going to start dropping off from there based upon the magnitude of our shear. So between here and here, it drops off by 1,012.5 pounds times 36 inches. So I'll plug that in here. 16,200 minus 1,012.5 times 36 inches gives us, oh hey, we're back down to here. 20,250 pound inches. So we're back down to here, and then we hit our reaction. Hit our reaction there. So again, that's a negative reaction. That's a negative point load. So again, when we're going from left to right, we subtract any moment point loads. So we subtract the negative point load, so add it, and that brings us back to 0, which is exactly where we expect it to be, which is a pretty decent sign that we solved the problem correctly. So based upon this, we know that so the largest magnitude of our bending moment is going to be right here. And we know that, again, we got a, it's a tube. So based upon that, we know that our bending stress is going to be equal to the moment times our y divided by a. So in this case, we're going to have a plus y and a minus y that are equal, and the outer points of this tube are an equal and opposite distance from the equal and opposite displacement from the neutral axis. So we can just plug in plus or minus 2 inches in for our y, and that'll give us the bending stress that we will see. So basically plug that in, the 44,550 pounds inch times plus or minus 2 inches divided by 8.59 inches to the fourth. So again, this inch and this inch cancels out to bring this to 2. And then we're left with PSI, and then that's a relatively large number, so I'm just going to go ahead and put it in KSI. So we will be seeing plus or minus 10.37 KSI at the point where this thing is mounted to the leftmost wall. So, and again, that'll be tensile on the top and compressive on the bottom. So again, so if we have a because our moment is negative when our so oh, here I forgot to throw another negative on there. I kind of ignored it a bit because because we're doing the plus and minus thing. But again, when we have we're starting out with a negative, and then when we throw a negative moment into there, then essentially that means that with a positive y, we're in positive tensile, and with a negative y, we are in negative compressive. So yeah, tensile on top, compressive on bottom is what happens when you have a negative bending moment at that point, whereas vice versa when we are talking a positive bending moment. All right, and that's about it.